got an RC circuit here. The input's this voltage source, and the output is the voltage across the capacitor. Our input consists of two sinusoids at different frequencies. 2 cosine of t, so omega is 1 radian per second for this component here, and 4 cosine 100t, so omega here is equal to 100 radians per second. So since we have two different frequencies, we have to basically do the problem two different ways because the impedance of this capacitor here depends upon the frequency. So to find y of t, do problem independently for each input, and then superimpose the results. So obviously, since these are sinusoids and we want to find the steady state response, we'll use the frequency domain. So circuit 1, for omega is 1 radian per second, we convert the circuit to the frequency domain. This phasor is 2 at an angle of 0 degrees. The impedance of the resistor is always just its resistance, so that's 2 ohms. The impedance of the capacitor is minus j over omega c, so this is negative j over omega is 1 radian per second. C is 1 over 20, so this becomes minus j 20 ohms. And then this will be the output phasor y1. Then we have to do the problem again for this input. So we have a second circuit. The frequency is 100 radians per second. At that frequency, the input is 4 at an angle of minus 25 degrees. The resistor's impedance is still just its resistance, so that's 2 ohms. The capacitor's impedance changes to be minus j over omega c, which is minus j over 100 radians per second times 1 over 20 farads, so this is minus j over 5 ohms. And this will be our output phasor y2. So we can use a voltage divider here and find y2. We can use a voltage divider over here and find y1. This voltage phasor will give us y1 of t. This voltage phasor here will give us y2 of t, and we superimpose those so that y of t is equal to y1 of t plus y2 of t. Now, this approach of analyzing each circuit separately so that we actually create a circuit schematic for the given frequencies can get really tedious, especially if we have 100 or 1,000 components that we have to superimpose here. There's an easier way to do it. We can just determine this as a function of frequency and then plug our different frequencies into the phasor representation here rather than determining the phasor from scratch for each different frequency. So let's go do that now. So let's take another run up at this problem, convert this circuit to the frequency domain, and leave omega, the frequency, as a variable. So we can plug 1 radian per second in and 100 radians per second in after we've done our overall analysis. This input is going to be u as a function of omega now, u of j omega. The impedance of the resistor is always just its resistance, so that's 2 ohms. The impedance of this capacitor is going to be 1 over j omega c, and this phasor here, y, will now also be a function of omega. The capacitor impedance is 1 over j times omega. I'm leaving omega as a variable, times 1 over 20 farads, so this is 20 over j omega ohms. Since I use j omega as my arguments here, I tend to leave the j and the omega together here. You can also convert this to minus j20 over omega ohms. I do this way more or less by force of habit. I can still use a voltage divider. So y of j omega in this circuit is the input voltage, u of j omega as a phasor, times the capacitor's impedance, which is 20 over j omega, over the sum of the capacitor and the resistor's impedance, which is 2 plus 20 over j omega. Doing some algebra, multiplying top and bottom by j omega, this becomes 20 over 20 plus j2 omega. Now in this expression, I can just plug in omega equals 1. In that particular case, u as a phasor of j times 1 radian per second is equal to 2 at an angle of 0 degrees. So the output phasor at 1 radian per second, y of j1, is equal to 2 at an angle of 0 degrees times 20 over 20 plus j2 times 1 radian per second. Simplifying that gives me 1.99 at an angle of minus 5.7 degrees. Taking this same expression at omega is 100 radians per second. In that case, the input u of j100 is equal to 4 at an angle of minus 25 degrees. Making a little more room over here and plugging 100 radians per second into this expression, y of j100 is equal to u of j of 100, 4 at an angle of minus 25 degrees, times this expression, which is just 20 over 20 plus j2 times 100 radians per second. Simplifying that gives me 0.4 at an angle of minus 109.3 degrees. So the output at 1 radian per second, I'm going to call y1 of t. That from this phasor is 1.99 cosine of 1 radian per second times t minus 5.7 degrees. From this phasor here, the second component, y2 of t, is equal to 0.4 cosine of 100t, that's its frequency, minus 109.3 degrees. Now I can superimpose these. The overall output is the sum of the two, so that's 1.99 cosine of t minus 5.7 degrees plus 0.4 cosine of 100t minus 109.3 degrees. And there's our answer. Now notice that you cannot superimpose these in the frequency domain. You can't superimpose the phasors. They don't have the frequency information in them, and you can't compare them directly one to the other. You need to get it back into the time domain before you do the superposition.